In this lecture, we're going to be taking a look at batteries. We're going to be taking a look at the interior structure of just a common battery, which is called a dry cell. And that's very different than what we looked at previously in the voltaic cell. Those were liquids that we're looking at. So batteries are called, the common battery is called a dry cell. We're going to compare a common battery to an alkaline battery, and then we're going to see what a true battery is, such as one that is in your automobile. So we'll take a look at those things during this lecture. So a common battery, again, is called a dry cell because we're not using the liquids. If you remember from the previous scenario, we had the voltaic cell, and we have a liquid here, we have a liquid here. And so this, of course, is not dry, so we're going to be having a dry cell in the common battery. I'd like you to draw this battery, and we're going to be drawing like maybe like a D cell battery or even a C cell battery. So they're shaped like cylinders. So it's like your flashlight battery, for example. And then it has this nub on the top. So if you were to look at the inside of a battery, this casing that's containing everything, this is actually made out of zinc. This outer casing is a zinc shell. Just like with our voltaic cell and even with the lab that we did, creating this electricity and creating voltage, we were using zinc. Zinc is going to be losing the electrons. So this is going to be the electron source. So over here, the electrons are going to be lost by the zinc. So the zinc is going to lose those electrons. If you're losing the electrons in this reaction, you are going to be oxidized. So in the oxidation reaction, this is the pitcher. It's throwing the electron. So this is the source of the negatives. So it's the negative side. Okay, so this is actually the anode. Now, I need to mention something that is very confusing, and it's all due to Benjamin Franklin. If you take physics, we're going to review this concept again. You don't need to know it for this class. But Benjamin Franklin, of course, you probably remember him with the kite and the key, and he was flying his kite in a lightning storm, which is not recommended because a French scientist tried to repeat his experiment and got struck by lightning and died. So please don't fly your kite with a key and try to replicate Benjamin Franklin's experiment. But what he did in his electricity experiments is he saw the jumping of a spark from one electrode to another electrode. So he saw this jumping or arcing of the spark. And what he did is, so he didn't know anything about electrons at that time, and so he didn't know that it was actually these electrons that were jumping. But since they were coming from one side and didn't know the charge or even the concept of an electron, he called that side the positive end. But actually, we now know that this is where the oxidation reaction is taking place. That's the negative end, and on the reduction is the positive end. So in chemistry, what we have is we have this anode, which is the true anode. It's the true anode because it's the source of the electrons. However, Benjamin Franklin called that the positive end. And all of electricity and all of the concept of electrical wiring and the whole field of electricity uses Benjamin Franklin's notation rather than the true chemical nature of this. So the electrons, what they do is they come from this shell, and they are transmitted into, the electrons are going to be traveling out through this nub. So they travel through the top of this. Now, this is actually the true anode, but if you look at a battery, what's the charge on a battery? The charge on the battery is a positive, so I'm not going to put a box around that. If you look at the bottom of the battery is the negative, but in reality, it is the positive. I hope this is not confusing you, but I just want to mention the top of the battery is the positive in case if you were looking at it, okay? But it's the true anode, and it's only the positive because that's what Benjamin Franklin named it. So I have to get that a little bit out of the way. So these electrons are going to be coming from the zinc shell. They're going to be going through this nub. They're going to be coming out and going into the wiring. They're then going to go into whatever device that you are using, a flashlight, for example. Then what happens is the electron comes from the device, and then there's wiring that's going to deliver the electron back to the battery. Okay, so the electron comes out, the electron comes back in. And when it comes back in, it goes to the inside of the battery, goes to either side. And what we have on the inside here is what's called an electrolyte paste. We have this electrolyte paste. This is why it's called a dry cell. It's because of this paste. This paste is filled with a bunch of ions. And here again, the zinc shell loses the electrons. Those electrons go through the nub, they go into the device, they come back, they come into this paste, and these ions are sitting there, and these ions are going to gain the electrons. So the electrons are going to be gained or received by this electrolyte paste. This is going to be your catcher getting the electrons. So this is where reduction is going to take place, and this is going to be the true cathode. So the cathode is, in chemical terminology, it's the positive end, but Benjamin Franklin called it the negative end. It's where the spark was going. And so since it wasn't the source, the positive source, he named it the negative. So just to repeat, this might sound very repetitive. The zinc loses its electrons. It goes through the nub, into the device, comes back in to the battery, goes into the electrolyte paste where there are ions. These ions are going to gain the electrons. And over here is the throwing of the electrons. So it's the oxidation reaction. This is the reduction reaction. So this is the same scenario that's taking place over here. We have our pitcher, we have our catcher. We have our oxidation, we have our reduction. We have our anode, we have our cathode. If you can get this picture in your minds, this will help you to remember all of these things. So what's happening with all these reactions that are taking place? Very, very similar to what's taking place inside the voltaic cell. Let's start with the zinc. The zinc, which is the solid, is going to begin to dissolve. And it is going to be producing zinc, okay? And this actually will then go into the paste as well. And it's also going to be producing the 2 electrons. So we can actually, if you want, you could put the 2 electrons that are moving along to power the device. These electrons then go into the device to be used. There's a force behind them, there's a push behind them that's going to actually power your device. So after that, the 2 electrons are going to return. So here's the return. And one of the ions is going to be ammonium, NH4+ ions. This is the paste. This is the catcher, and it's a positive ion. And this is what is filling up the paste. You might remember this ammonium ion when we were looking at polyatomic ions. So the ammonium ion is the true cathode. It's catching the electrons. And when it catches the electrons, well, previously what happened is we have this copper ion, which is capturing the electrons, and it becomes solid copper. What's happening here is when the electrons come in, this causes the ammonium ion to become NH3. And this is going to be ammonia. This NH3 is going to be in the gaseous form, and so it's producing ammonia gas. So now what's happening is you've got this container, which is the battery, and it's starting to fill up with ammonia gas. What's going to happen when a gas starts to fill this sealed container? This is going to build up pressure. So we increase the pressure on the inside of the battery. Okay, let's take a look at what's happening. What's happening to the strength of our battery? Because the zinc shell is beginning to dissolve as the electrons are being lost. So this zinc shell is going to weaken. So the combination of our container, which is getting weaker, and we also have the increased pressure building up on the inside of the battery, what's going to happen to the battery? The battery is going to, quote, explode. When it's exploding, what it's doing is it's actually leaking its contents out because the shell has eroded and it's built up this ammonia. And what's leaking out is a combination of ammonium ions, it's going to be a combination of zinc ions, and it's going to be whatever else is in that electrolyte paste. So that's a common battery. Let's take a look at what alkaline batteries are. I'm running out of space here. So alkaline batteries, this has the same structure as your common battery. So it's still a dry cell. So it has the same structure, except instead of having a paste that's filled with ammonium, which is NH4, the paste is filled with something else. The paste is potassium hydroxide, KOH. Well, we learned from the previous chapter that things with OH are bases. And another name for something that is basic is alkaline. Alkaline means basic. You might be testing the alkalinity of your pool, for example, and that's testing how basic it is or how acidic it is. So the opposite of acidic is going to be alkaline. That's why it's called an alkaline battery, because we're using this paste has a base in it. So it's the whole same process. We have the zinc. The zinc produces the electrons. The electrons go into the device. The electrons come back. So now we're going to pick up right here. So here the electrons are coming back, and we have the two electrons. But instead of the ammonium ion, we have the potassium hydroxide. So in this potassium hydroxide, we have a mixture of other things as well. The reaction from this is the electron will jump onto the OH with an additional H, and it's going to create water. So the summary of this is that we're not building up gas pressure. So since we have no ammonium gas being produced, we don't see an increase of pressure. So while alkaline batteries can explode, they explode less often than your common dry cells. Alkaline batteries tend to be a little bit more expensive as well. So these guys are going to have less leaking. Will they still leak? Yes, they can still explode like your common one, but it'll be less likely to do so.